Okay, good. Hello. Thank you, everybody. Thank you for joining us. We are delighted to be here with you. I'm Dr. Stephanie Brown. I'm Managing Director of Clean Water Wave, a social enterprise based here in Scotland where we are at the moment, that's developing sustainable and nature-based water treatment solutions. I've worked extensively across East and Southern Africa in particular, and I've seen a lot of unsavory things around water and sanitation and water pollution in particular. And I first met Howard around 6 years ago, along with our co-founder, Diane Duncan, without whose passion and vision, none of our work at the moment would be even happening. I was completely bowled over when Howard told me about his work in the UK and across South Asia and East Asia in particular, and about the dire state of our water resources and the things that he'd seen in his work that really flagged to us the significant and worrying implications that pollution is having for the health and viability of our planet. So today we will be delving into Howard's work and background and the implication that pollution is having for planetary health, and of course delving into the Global Oceanic Environmental Survey and the citizen science project at the heart of it. But first, just a bit of housekeeping. We hope to be discussing for around 40-45 minutes, and then that we'll get some questions from you guys afterwards. So please, if there's anything that we discussed that you're interested in finding out more about, please just pop them in the Q&A box at the bottom. And our colleague Caroline in the background, hi Caroline, will be collating the questions for us. And afterwards, if there's anything you want to follow up on, or you've got any kind of questions or collaboration opportunities, or you've got some research that we've got synergies with, then please do get in touch with us and we'll say more about that at the end. But for now, my guest and star of the show is Dr. Howard Dryden. He's a marine biologist by background, and he's also an entrepreneur, and he's been active in solutions for water treatment and within the water sector for over 30 years. And you've really traveled the world doing water treatment systems, really investigating issues with water pollution and problems in the water sector. And really, you've been active in every single trajectory that I think it's possible to be exposed to in the water sector. So Howard, would you start off, please, by giving us a little bit more about your background and why you are really uniquely placed, I think, to comment on oceanic health and climate change?
Okay, thank you, Stephanie, for that wonderful introduction. I'm not sure if I can live up to that.
I'm sure you will.
Well, this journey, it starts for me, some 30, nearly 40 years ago now. And I did a PhD in Edinburgh on water treatment for the fish farming industry. And what we were doing was doing research on closed system aquaculture. Now, what that really means is that we can take a fish farm, really almost any species of fish or invertebrate, and grow these animals in tanks and recycle 100% of the water. And we did that in Edinburgh. We grew over 100,000 salmon in the middle of Edinburgh and about 20 tons of eels, while I was a student. And it was great fun, and we learned a great deal about water chemistry, water quality, and the biology of the whole process. Unfortunately, the PhD I was doing, was on a special type of sand called a zeolite. And very quickly into my research, I found it wasn't entirely suitable for the application. This often happens with research. You start off doing something and you realize it's not entirely what you had expected or hoped for. So as a secondary piece of research I was doing in parallel to my PhD, I thought, well, as a naive student, let's try and reinvent sand. So, completely ridiculous, but you're allowed to do these things when you're a student. And so what I thought, well, glass is made from sand. Why not turn glass back into sand and re-engineer the structure of the glass to take out certain chemicals from the water? And unbelievably, that's what I did when I was a student. I managed to recycle glass bottles and turn it back into sand, but I made the sand actually work a great deal better than regular sand. And I actually formed a company on the basis of that. And over the last 30 years, we're now actually upcycling more than half the glass bottles in Scotland, or coloured glass bottles. And a new factory has opened up in Switzerland as well. So we're now the biggest filter media manufacturer in Europe. And it all stemmed from a failed PhD. But anyway, that the filter media called AFM, active filter media, allowed me to get into many different industries around the world. One of the first and primary ones for us as marine biologists, dealing with the life support systems for aquaria is always great fun. And we've actually been involved in the design and running of over 100 of the world's largest marine aquaria. Examples include the Lisbon Aquarium has our filter media, and I designed the Istanbul Aquarium. We also have Dubai Mall and the Burj Al Arab and many, many more. But what that taught us was that marine aquaria are like a proxy for the oceans. We're dealing with thousands of cubic meters of water with hundreds of different species of fish and invertebrates, all living in this kind of community. Now, in parallel to that, I was also working on water and wastewater applications. One I really enjoyed doing was the textile industry in Bangladesh. Textiles account for about 80% of the economy of Bangladesh, but they have managed to completely destroy most of the water supplies. 100% of the surface water in Dhaka, which is a city of 20 million people, totally destroyed. And 90% of the groundwater is destroyed. So I was involved in water treatment systems to treat the textile wastewater and minimize or prevent the impact this effluent has on the environment. And we did that. We managed to do it. And at the same time, or following on from that, I was also working in China on pharmaceuticals, and Taiwan on the steel industry, to West Bengal working with effluent going into the Ganga. So covering this wide range of diverse environments and different water types. And I began to realize, well, there's a huge amount of horribly toxic waste going into our rivers and going into the seas. And the realization that, with the big public aquaria, the merest pollutant in these systems can have a devastating impact, on the animals and the plants. And I thought, well, the same thing must be happening in our oceans.
Right. Okay. So, I mean, it sounds like you've been unbelievably busy over this period of time, from this, what you call a failed PhD, which has actually turned into a huge success. But what you're really saying is that these kind of huge, tiny changes in water chemistry that you were seeing were having a really big impact on the viability of marine life. But what does this actually have to do with climate change? Why are we here having this discussion today?
Well, that climate change is like an equation. What goes into the atmosphere in terms of carbon dioxide has to come back out of the atmosphere again. Mm-hmm. And the entire world is really focused on carbon mitigation, windmills, electric cars, reducing CO2 emissions, and almost totally we've neglected nature and the mechanisms for removing carbon dioxide from the atmosphere. Mm. Now, this really brought into focus, for me. I was attended a UNESCO conference in Europe, in Paris, in June 2019. 500 of Europe's top marine scientists. And to be honest, I was shocked by what I was listening to. By way of example, the three top or key points that came out of that conference. Number one, or say number three, was it was nice to live by the sea. My God,
anodyne.
A conference with 500 marine scientists, and that's all they could come up with. The second one was that we're doing a really good job of cataloging the destruction of the oceans. Well, what about the protection of the oceans? And the first point, or the last point in this case, was that the UN didn't consider the oceans important with respect to climate change up until 2015. And I thought, my God, the oceans actually produce all or 99% of our oxygen. Every breath you take will have come from marine plankton in the oceans. They have absorbed 30% of all CO2 that man has ever emitted. So absolutely the oceans are important with respect to climate change, yet they have been ignored.
Yeah, I know. I find that, extraordinary, actually, that, given that we live on a blue planet, but the oceans weren't really considered by these agencies until, as you say, 2015. But can you give us an idea then about why it is that the dominant train of thought around climate change has been so focused on terrestrial ecosystems, trees, and carbon. But actually what you're saying is that really we have to focus on the oceans and on ocean plants rather than terrestrial plants, and that these ocean plants really have been ignored for far too long.
Yeah, absolutely. Well, most people think that the Amazon rainforest are the lungs of the planet. Nothing could be further from the truth. The Amazon rainforest actually is a net exporter of carbon dioxide, huge exporter of carbon dioxide because of the burning of the trees. But even if we weren't burning trees to clear it for farmland, mature established forests such as the Amazon rainforest are in perfect balance. When the trees are growing, they're removing carbon dioxide from the atmosphere and producing oxygen. But at the same time, there are trees that reach the end of their life, and when they die, they decompose. The bacteria and fungi use oxygen, exactly the same amount of oxygen that the trees produced when they were growing, and they also release carbon dioxide in exactly the same proportions. So most mature ecosystems or forests or terrestrial ecosystems are in balance. So they don't produce oxygen and they don't remove carbon dioxide from the atmosphere. There is some CO2 absorption in the soil, but if we take just above ground, then the net effect is zero. But also let's put this into perspective. When trees are growing, or when leaves are growing in springtime, and when grass is beginning to sprout, then 1,200 gigatons of CO2 are taken out of the atmosphere with this new growth in springtime. And equally, during the autumn, when leaves are falling off the trees and grasslands are dying back, then 1,200 gigatons of CO2 goes back into the atmosphere. Now, these are really big numbers, but to put this into perspective, the burning of fossil fuels by man contributes 10 gigatons. So the burning of fossil fuels only equates with less than 1% of what terrestrial nature puts into the atmosphere and removes every year. Now, out of that 10 gigatons of CO2 produced by man, 5 gigatons are sequestered by nature. So we have climate change because of this 5 gigatons of CO2. What I find surprising is that there is no flexibility in nature, that there is not the capacity to absorb this very small amount of extra carbon dioxide from the atmosphere. And that tells me that there is something not right. There is something wrong with nature, and that nature is currently under stress.
Right. So just forgive me if I've got this wrong here, but I think it will help clarify it to our audience. But what you're saying is that terrestrial ecosystems, basically on land, really that they aren't that important for climate change. I mean, that sounds quite controversial, but that's kind of what you're saying, right?
No, in terms of CO2 sequestration and oxygen production, then yeah, they're not that important. Technically, you could cut down every tree in the planet and remove all the grasslands. It will make no difference really to climate change in terms of the CO2. I absolutely do not advocate doing that for a second. Because trees and plants are critically important. Now, if we take the example of the Amazon rainforest again, with all these trees, there's a process called transpiration, where water is put up into the atmosphere, from the trees. They're also producing a chemical called DMS, dimethyl sulfide, which seeds clouds. So forests like the Amazon rainforest actually create ecosystems. They create clouds, and those clouds reflect sunlight. They reflect energy back into space. So if it wasn't for this cloud formation in the Amazon rainforest, then the climate would be very much warmer. And we know this. The catastrophe that happened in 9/11 grounded most of the world's airplanes for a few days, so I think it was up to a week. And just focusing in on the American cities, because the planes were no longer flying, there was no contrails. And because of that, more energy was getting into the cities. So temperature actually rose by about 3 or 4 degrees centigrade. Then when the planes came back online again, the contrails were reflecting the the energy back into space, temperature dropped. So cloud formation, critically important. Forests are also important for putting organic matter into the soil, but that's a different issue. But keeping with the terrestrial ecosystems, the really important in terms of climate change and CO2 fixation are the wetlands, marshlands, peat bogs, mangrove swamps. That is where our carbon or terrestrial carbon is deposited, and that's where our oxygen is produced on the terrestrial ecosystem. And to put again that into perspective, mangroves only cover about 0.6% of the terrestrial or landmass, yet they are responsible for 30% of all terrestrial oxygen production and CO2 fixation. And the marshlands and peat bogs are responsible for the rest. So it's critically important we look after our wetlands.
So we're protecting these key environments then on land. But you were saying a bit earlier about the lack of resilience in nature to deal with these changes that you were talking about, and that you're really sort of, I think, thinking through ideas around temperature and pollutants that are putting nature under stress. What has led you to these kind of conclusions then?
Well, working with the marine aquarium industry and aquaculture systems and water and wastewater, you begin to see pictures developing or patterns developing. And we were involved with the Greek fish farming industry some 20 years ago. And they rely heavily upon sea bass and sea bream, as a commercial aquaculture product. But they were finding that it was becoming impossible to grow sea bass. The small fish couldn't get past 1 gram in size because they were getting disease. And what we found was that the alkalinity of the water, that's the carbonate content or bicarbonate content of the water, had dropped slightly in the Eastern Mediterranean. And that allowed the pH or acidity of the water to drop very, very slightly as well. And that made a virus called a norovirus pathogenic to the sea bass when they got to 1 gram in size. So as soon as we realized what was happening, we were able to fix the water. And then there was no problem in growing the fish. And that actually saved the entire sea bass fish farming industry in Greece. And it was because by a change in chemistry of the water. Now, I can give you another example with regards to the aquarium industry. These big public aquaria, will have anything from 5 to 40, 4,000 cubic meters of water. So huge systems. But if you were to put a 1 meter section of PVC pipe somewhere in that water treatment circuit, then you would probably kill all the fish.
Yeah, I find that absolutely mind-blowing, and we'll come back to that plastics issue in a moment. But I'd like to turn to temperature, as a lot of the discourse that we hear around oceanic ill health is specifically about temperature. That's kind of what we hear in kind of public discourse, is that the seas are warming, so the seas are sick, and that's having an impact, particularly on our corals. That's often what we read about and hear about. But you don't think necessarily that the rising oceanic temperatures is what is the key stressor for our corals, is that right?
Well, an increase in temperature obviously is important for the coral reefs, but there are other factors involved as well, and other stressors. But just looking at the coral reefs, we've lost more than 50% of the world's coral reefs over the last 20 or 30 years. And that's really important because 25% of all marine life living in the oceans depend upon the corals as nursery grounds. Yeah. So it's absolutely critical that we protect these environments. Not only that, about 0.5 billion people depend upon coral reefs as a source of income, tourists, but also for the fishing sector and also for coastal defenses. So coral reefs are really, really important. And it's tragic that we've lost more than half of the coral reefs, and we could lose 90% of them over the next 10 to 20 years. Now, this has been put down to climate change, to global warming or increase in temperature causing bleaching events. What we now know is that it may not be the case, because what we're finding is that coral are incredibly sensitive to certain chemicals, photoactive chemicals. the chemicals that you find in sunblock.
Right, so they're photoactive on our skin, presumably also photoactive in the sea.
Absolutely, and the way these chemicals work, such as oxybenzone, is they don't block the sun. They simply just change the wavelength from a damaging, ultraviolet wavelength to a slightly longer wavelength that doesn't cause the damage to the skin. But in so doing, they release a toxic chemical called a hydroxyl radical. So what happens in the sea by coral reefs is that people go in swimming, the sunblock or some of the sunblock washes off and it forms a film on the surface of the water. Some of this chemical gets absorbed onto particles like microplastic. And then the microplastic concentrates the chemical many thousands or even millions of times. And then coral are small animals and they're grabbing particles out of the water. So when they grab a particle of plastic, they're grabbing all the chemicals as well.
Right.
Now that the chemical's inside the coral, exposed to sunlight, the oxybenzone does what it's meant to do. It blocks the UV light, generates free radicals. This really upsets the coral. So it dumps its symbiotic algae. Algae live inside coral. And this makes the coral bleach. It's called a bleaching event. It then is very sensitive to elevated temperature.
Right.
But if the coral had not lost its symbiotic partner, then it would be resilient up to much higher temperatures, and we would not be seeing these coral bleaching events.
Right. I mean, that's, I think that's really fascinating and particularly pertinent because we're seeing now chemicals like oxybenzone being banned by particular island states, Hawaii being a good example of that. But we also see that there's a lot more research around kind of the pervasiveness of toxic chemicals like oxybenzone, and it's in a lot of products, right? It's in a lot of cosmetics, it's in makeup, it's in obviously, as we said, SPF sunscreens and other personal care products, and it's also present in plastics, right? Can you tell us a little bit more about just how toxic oxybenzone is from the work that you've done?
Sure. Well, there are perhaps about 10,000 other chemicals that are equally as toxic as oxybenzone, but let's just focus on this one because most of the really toxic chemicals all have a similar characteristics, and many of them are what we call hydrophobic or lipophilic. That means they're oil-like, they behave like an oil. And oxybenzone is toxic at a level of 60 parts per trillion, which is a really, really small number. To put this into perspective, that if you had 70,000 tons of oxybenzone and you dissolved it into the world's oceans all at the same time, you kill everything. Nothing will survive that concentration. But remarkably, we put 20,000 tons into the ocean every year from sunblock. And that's why the corals are dying.
So just reiterate that for a second, 70,000 tons of oxybenzone would kill everything in the oceans. And annually, we're already putting in 20,000 tons.
That's right, from bathers using sunblock on the beaches. But what's even more disturbing is that the world actually manufactures 1.5 million tons of this one chemical because most plastic contains oxybenzone as a UV stabilizer. So that's another reason why plastic is so horribly toxic to the environment.
Right. So really what you're saying here is that corals are not dying because of temperature increases, but actually because of this combination then of these toxic chemicals, because of plastics and of ocean acidification. Is that?
Yeah, that's it. Most animals don't suffer just because of one factor. Right. Usually it's an accumulation or a multiple number of factors. But when you know something is that horribly toxic to the environment, then you think you do everything possible to try and remove it from the equation. But we're making more and more of this chemical every year. And more plastic.
And you talked about corals taking in plastics, or microplastics as food, effectively, mistakenly thinking that it's something delicious to eat. Is this also happening with other oceanic plants and animals?
Yeah, this is a key point. Just taking the Atlantic Ocean, a recent report said there were 21 million tons of microplastics in the Atlantic Ocean. Now that equates with 7 particles of plastic in every litre of water from the surface down to a depth of 200 meters. Now, there's another organism which nobody had probably heard of. It's called Prochlorococcus.
It's quite a name.
Yeah, it's actually a bacteria. It's got a bacteria with chlorophyll inside it. In fact, you wouldn't be, most people haven't heard of this. Indeed, the world hadn't heard of this organism up until 1985, because it only measures 0.6 microns in size. Yet there are more cells of Prochlorococcus than there are grains of sand, and it produces more than 20% of the world's oxygen and removes 20% of the world's CO2. But we didn't know about it until 1985 because it is so small. And most plankton nets used by oceanographic ships measure about 60 to 100 microns, and it was simply missed. But we now know that microplastic is horribly toxic to Prochlorococcus. In fact, not microplastic, it's nanoplastic. It's even smaller particles, because the nanoplastic actually can go through the cell membrane of these bacteria and kill it from the inside. So, we're learning more and more about this every day, but it's critically important that we address these issues.
So what I'm hearing from you is that really that we've got this kind of chemical soup effectively happening in our oceans, and that this is really having a massively detrimental effect on our oceanic plants and animals. And it's really, I would guess, the kind of lead on point from there is that it's actually not only killing all our plants and animals in our ocean, but also preventing our main mechanism as a blue planet for carbon sequestration, for storing carbon. Can you tell us a little bit about how that?
Yeah, absolutely. Well, I'll backtrack a wee bit here as well. I talked about Prochlorococcus and algae. I think it's also useful to mention the animals that live in the ocean as well. In particular, what's called the zooplankton, because remarkably, 60% of all life in our oceans is under 1 millimeter in size. And one organism in particular called the copepods. There are 5 gigatons of these animals living in our oceans. That's 10 times more than all terrestrial animals combined. It's a really difficult number to conceive what 5 gigatons actually is, but it's equivalent to 17 million jumbo jets. And if you were to put these jumbo jets nose to tail, they'll go around the world 30 times. So that's the number of animals that we've got living in the ocean. And these organisms, they migrate from a depth of 400 meters below the surface, up to the surface every night to feed on the Prochlorococcus and the algae. And they actually eat 30 times more carbon than man burns from fossil fuels. And when these organisms defecate, their waste, if only 6% of it reaches the abyss, that locks out 3 gigatons of CO2, which is 30% of all the CO2 produced by man. So it tells you that the marine ecosystems and organisms are hugely important. And indeed, the oceans have absorbed more than 30% of all the CO2 produced by man. But if you don't have the plants and animals there to use that carbon, then it starts to build up in the oceanic water. And when you dissolve CO2 into water, it forms another chemical called carbonic acid.
Right. And
that starts to drop the pH of the oceanic water.
And that's really what you're talking about when we think about ocean acidification. Is that correct? And what we're talking about when we think about ocean acidification, it's really this CO2 in our atmosphere that gets absorbed into the oceans and it lowers the pH. But I mean, I think you spoke at the top of our conversation about how these tiny changes in water chemistry have, pretty massive impact. And you saw that obviously from your work, particularly in the aquarium. But so can you tell us a little bit about how these changes in pH then are having a massive effect on our oceans?
Sure. Well, ocean acidification is often referred to as the evil twin of climate change. It's called the evil twin because in many respects it's even more serious than climate change, and it's happening now. So, if we go back to the 1940s and 1950s, I'm sorry, I'm going to read a bit chemistry here. But
everyone's learning lots of good words in chemistry today.
Okay. Well, I'll try and avoid it. But the pH, it's a measure of the alkalinity and acidity of the water. the pH was 8.2 during the 1940s, 1950s. But over the last 70 years, that pH has dropped to 8.04. If we then project forward the next 25 or 30 years, it will drop down to pH 7.95, 7.9. Now, that doesn't sound like a great shift in pH, from 8.2 in the 1940s to 8.04 now to 7.95 in 25 years. The issue is that more than 50% of all marine life is based on a form of calcium carbonate called aragonite.
Okay.
Now, it's like if you take vinegar and you put it onto chalk, or you add lemon juice to sodium bicarbonate, it will fizz. Well, that's what starts to happen at a pH of 8.04 to calcium carbonate. The organisms made from this mineral start to dissolve. It's already started, and by the time we reach a pH of 7.9, 7.95, it will essentially be complete. So what we're looking at is a potential loss of more than half of all marine life.
So I think we just need to extrapolate this a little bit for our audience. So what you're saying then is these, what sound like relatively small changes in oceanic pH are going to have catastrophic effects on the majority of marine life. And that's primarily because the majority of marine life is entirely or partially composed of this thing called aragonite, correct?
Absolutely.
Okay.
So,
what is it? Tell us a little bit more about aragonite. Animal, plant, bones, shells, what is it?
Okay, well, where we're at the moment, oceanographic surveys have already confirmed that since the 1940s, we've already lost more than 50% of all marine life. And it's currently declining at a rate of 1% year on year. And we know that when we reach this, what's referred to as the tipping point of pH 7.95, then there'll be a catastrophic loss of marine life because it's based on carbonate, which is dissolving. And it's really almost basic chemistry. There's nothing that can be done. These animals cannot survive this. And the marine ecosystem is all connected, like many complex ecosystems are. If you take out one group of organisms, it will have a chain reaction, it will have a knock-on effect. So my fear is that within 25 to 30 years' time from now, if we continue to lose marine life at the current rate, then within 25 years, we're down to about 80%, loss since the 1940s, with no ability to remove the carbonic acid from the water. So at that point, we fall off the cliff, with the potential loss of all the seals, marine birds, whales, all the fish, and with that, the food supply for more than 2 billion people. And it's happening.
Yeah, I mean that sounds absolutely, well, quite frankly, it sounds terrifying. So really what you're telling us is that we're going to lose, we're reaching a tipping point with animals effectively starting to dissolve because of these changes in the pH. And we're hearing then again now starting to talk there about the consequences of this. But what I think we hear from a public policy perspective is a lot about net zero, and the net zero seems to be our be all and end all solution, I guess, for saving our planet. But really, what you're saying is that is not the case at all. I mean, you haven't even touched on net zero as a solution. So, tell us about why that isn't the case. Why that isn't our solution.
Okay, well, if we continue with what's referred to as business as usual, and don't reduce the production of carbon from the burning of fossil fuels, the IPCC call this RCP 8.5. But business as usual, then within 25 years, the world will hit, or the oceans will hit a pH of 7.95, with the atmospheric levels being in excess of 500 ppm. Now, if we achieve net zero, and Europe is aiming to achieve net zero by 2045, but let's say we achieve net zero for the world by 2030. That is RCP 4.5. Now, that will be completely impossible to achieve that level of carbon reduction. But even if we did achieve RCP 4.5, then atmospheric CO2 levels will still hit 500 ppm. and the oceans will still drop to a pH of 7.95, albeit 5, maybe 10 years later. It's not going to work. There is nothing that we can now do in terms of carbon mitigation to prevent a trophic cascade collapse of the entire marine ecosystem.
Okay, well, I mean, Howard, this is, it's mind-blowing really what you're talking about, but also, obviously extremely concerning for all of us, and the reason why we're all involved in doing this, in doing the GOES project. But I think, from knowing you and working with you, that there's a positive story to be told from this, that it's not all the doom and gloom that you've just given us. Can you tell us a little bit about why actually this research and this work, although sounds really terrifying, actually it's an extremely hopeful story?
Well, it has the potential for being a really good news story once you understand or have a handle on the mechanisms involved. And it's all about eliminating pollution and regenerating nature. We need to bring nature back because it's nature that was responsible for the production of all our oxygen and for the removal of the CO2 and for cleaning up our environment. But before I get on to that, I just want to mention also the terrestrial ecosystem, because whatever happens on land, impacts on the oceans. Every action on land, will have a knock-on effect. And another area that's of great concern are insects. We depend upon insects on land, but same as happening in the ocean. We have lost more than 50% of all insects. And indeed, we have lost more than 80% of all flying insects and pollinators. And they're dying off at a rate of more than 1% year on year. So within the next 20 to 25 years, we could effectively have wiped out all pollinators. Agriculture then collapses. Yet we continue to use and license very toxic herbicides and pesticides, such as neonicotinoid. Recently Europe banned this chemical, which is horribly toxic to bees. But I understand today they have permitted the use of neonicotinoid for treating parasitic infections in the aquaculture industry. Well, that's really clever. One of the most toxic chemicals in the world, and we're now dumping it into the oceans. So really, we have to detoxify the world. We can no longer continue to use these toxic forever chemicals, and we have to restore and bring back nature. Now, if we're dealing with that on land, it takes decades for trees to grow and for terrestrial plants to grow. And indeed, if we're to put a measure on that, to double the biomass of trees and plants on land takes about 60 years. But remember, I said that most marine life in the oceans is under 1 millimeter in size. And many of the organisms are actually bacteria that can double in biomass in minutes. So the average doubling time for all life in the oceans, taken collectively, is 3 days.
Wow. Okay. So not only are our oceans vitally important for our climate, but they also hold the potential for being able to deal with what we're seeing from a climate change perspective.
Absolutely. So, if we have 10 gigatons of CO2 going into the atmosphere from the burning of fossil fuels, and currently the oceans are removing about 3, maybe 4 gigatons of CO2. If we take the brakes off the marine ecosystem and restore the oceans to the condition they were prior to the 1940s, prior to the time which I refer to not the Industrial Revolution, but the Chemical Revolution, when we started manufacturing plastic, when DDT and herbicides and pesticides, these toxic forever chemicals started to be produced. If we wind the clock back to before that time, then marine productivity was twice what we have at the moment. So technically, if we eliminate the pollution for the environment by eliminating these chemicals and by reducing or eliminating plastic going into the oceans, then we can double marine productivity and potentially raise that sequestration rate from 3 or 4 gigatons up to between 6 and 8 gigatons. So we're only a very small part away now, from being totally carbon neutral. The world drops its carbon budget by 20%, then we're carbon neutral. And at the same time, with the extra biomass and growth in the oceans, then we can remove the carbon or the carbon dioxide and prevent the oceans going acidic. So we save the oceans and potentially climate change.
So a real positive story then to actually come out of this is that, you know, the answer to really all of our problems is a focus on the ocean, a focus on regenerating nature, and really a focus on detoxifying our environment. And I guess that's really what leads us to GOES and where GOES comes into. So that GOES is the Global Oceanic Environmental Survey. So tell us a little bit about what the mission of GOES is and what you are up to with this.
Okay, well, you know, it's important to try and identify, you know, where the problems are coming from. You know, what is the source of the pollution? And I think everyone really knows, you know, where the pollution is coming from. And one of the primary ones is actually municipal wastewater. You know, 80%, or in fact, only 20% of the world has effluent wastewater treatment. And if we take Europe and North America as an example, you know, we have you know, municipal wastewater treatment, but only a very small percentage, less than 10%, have what's called tertiary treatment to remove plastic. You know, and I think that's shocking that you know, the water industry say they're removing plastic from their wastewater, but in reality, you know, well, indeed, they're moving maybe 90 to 95%, but even 1% of the plastic going into the oceans is way too much. But that other 90% ends up in the bacterial biomass, or what's called sludge. And that goes back onto land, or it goes into landfill sites. Then eventually it gets back into the environment again. So it's not treatment, it's just dispersed disposal. So we have to eliminate pollution from municipal wastewater treatment plants and have them being zero impact.
So then with GOES, you've got a lot of this, as you were just talking about, a lot of the advocacy and research side of this, but you're also about kind of educating and collecting evidence to develop what you've just been talking about in terms of pollution and plastics. And I believe that as part of, you know, something that's really key and really at the heart of what you're trying to do with GOES is undertaking a citizen science project. Can you tell us a little bit more about that and what you're gonna do and what that's gonna tell us?
Yeah, absolutely. You know, it's again just raising awareness and collecting the information. But before I get on to that, I think I'll just quickly mention some other sources of pollution that we have to address, and then we'll go on to that question. So we've got municipal wastewater. There's also storm water. You know, every time it rains heavily, all the roads get washed, and the plastic ends up again in the rivers.
I think you might even have to just explain that bit, because maybe a lot of people don't, you know, plastics from road.
Yeah,
how does that end up in our water? Where do the plastics come from in our roads?
You know, roads are, you know, highly polluting to the environment. Car tires, you know, car tires, when you're driving a car, you leave plastic on the road. And also some of it goes up into the atmosphere, and it's the biggest contributor for microplastic are car tires. Not only, you know, is it are these particles, you know, well, actually they're incredibly toxic to marine life because they contain antioxidant chemicals, which are, you know, extremely toxic. But there is no treatment for it. It's simply washed off the road directly into our rivers. And this has to stop as well. Now, the other aspect of it, a lot of the plastic goes up into the atmosphere, and the particles get picked up by the Earth's magnetic field and gets drawn down at the polar caps. So a combination of this black rubber plastic, along with the carbon soot from diesel engines and coal-fired power stations, is actually turning the Arctic black. And what that is doing is that, you know, if you have nice white snow, it reflects most of the energy back out into space. But if you have discolored snow and ice, it absorbs energy and it melts. Right. And this is actually one of the principal reasons why we've got the melting of the polar caps. It's not all climate change. It's not all about heating up the atmosphere. It's actually changing the color of the snow because of all the black particles that are in our atmosphere. So there are many things like this, and there are solutions, you know, green chemistry for cosmetics and pharmaceuticals, new compounds for the car tires. And indeed, electric cars, you might think are the savior, but they're actually heavier. They're 50% heavier than conventional cars, and they go through the tires much quicker. But what And there are solutions for this. There is actually an alternative type of tire which is non-polluting. And it's actually made from, I believe it's dandelions. And they make a plastic out of the dandelions. Don't know how they do that, but it's not being promoted because the companies don't make so much money out of doing it. But I think if the public were aware that that option was available, then it would be a more economic alternative.
So really with GOES, then it's a lot about identifying these different sources of pollution and the impact that it's having on the environment, and then developing and raising the awareness and developing this.
Yeah, and that then comes to our citizen science project. Most of oceanographic ships have been doing a great job over the last 50 years or so in modeling what's happening in the marine environment, but these ships are horribly expensive to operate, and very rarely do they go out into the middle of the Atlantic Ocean or the Pacific. Hence the reason why we didn't even know that a bacterium algae called Prochlorococcus didn't exist, till 1985, or we weren't aware about it. It's because the ships don't go out into the middle of the ocean all that often. We are aware that there are in the region of 21 million tons of microplastics in the Atlantic Ocean, but we don't know the dynamics between the plastic and the plankton.
Right.
So what I want to try and use and work with are those yachts or blue water yachts which are crossing the Atlantic and the Pacific and the Arctic oceans, and to collect small samples of water and then filter the water samples. We've designed a new type of filter which will filter half a litre of water, and then still on board the boat, we count the number of particles of plastic in plastic fibers, and also count the number of zooplankton and phytoplankton. That's the animals and the plants. Okay. So we start to hopefully build up a picture of what is actually happening in the middle of the ocean.
And so this work with the sailors, these are just ordinary sailors. They're not research boats that are going out. These are just people that enjoy sailing and happen to be crossing the Pacific and the Atlantic, right? That's who you're trying to recruit, really.
Absolutely, anyone can do this. Okay. We're focusing on the blue water yachts because we're really keen to see what happens out in the middle of the ocean, because there's a lack of information, from these areas, and in order for informed decisions to be made, then we need as much information as possible. And sadly, it's lacking in that department at the moment. We know it's happening. There are many peer-reviewed reports on this as well, but we need to fill up a few holes in that.
And so when people are doing their sampling using the tool that you just demonstrated, and that you said that they'd be looking at plankton and zooplankton and microplastics in the filter, how easy is it to differentiate between these things? I mean, for me, who's not a marine biologist, can I do this work?
Yeah, well, on the GOES website at goesfoundation.com, we're preparing all the information that allows anyone to do this work. Now, seeing microplastic can sometimes be very difficult, but usually the microfibers are more common than the microplastic, and they're really easy to see. And when we were doing the first trial run across the Bay of Biscay, we're actually finding more microplastic fibers than zooplankton in the water. It was absolutely horrific. Middle of the Bay of Biscay, it's another garbage patch for plastic. With the animals, not a problem seeing them, especially the copepods, because what we're doing, with the small onboard microscope is looking for everything down to about 20 microns. That's a pretty small number. 1 millimeter is 1,000 microns, so 20 microns is 1/50th of a millimeter. So everything down to that size, and most of the plant life and animal life is bigger than 20 microns that we're focusing on. Obviously, the bacteria are much smaller, but we have to draw the line somewhere, and it's not practical to have a high-powered microscope on board a yacht. Yeah,
so it's trying to make it practical and but also extremely useful from a data perspective. And am I right in thinking that you're developing an app so that people can geolocate as well, so we know where they're getting this data from?
That's it. Well, initially it will be in paper format, so we'll record the GPS position of the boat and also number of particles of plastic and zooplankton. So I prefer to have things on paper, but we're also in the process of developing an app for it as well.
Okay. So if our audience at all want to get involved and they have access to a yacht and they're seafaring, what do they do to take part?
Yeah, well, go on to the goalsfoundation.com website and drop us an email. And we'll get back to you. But really, all the equipment required here is that we've identified it and put a link to Amazon, so you can purchase your own microscopes and equipment. We manufacture the filter. So for the first 100 filters for ocean-going yachts, we're happy to give the filter away free of charge. If we have to deliver it, then there'll be delivery cost involved with it. But if people can collect, either from Edinburgh or from our Tenerife office, or from directly from our research boat called Copypod, which is currently in Portugal, then we're happy to donate the filter for yachts.
And what if people don't have access to a yacht, which I would assume is going to be most people? What can people do to help?
Well, actually, still with the plankton sampler, it is also for microplastics. And what I've been doing here in Edinburgh is actually measuring our local river and counting the amount of plastic that we're getting in our local river. So, as I said, pollution starts on land. So monitoring the rivers are also really important. More disturbingly, I've been measuring our own municipally supplied tap water and also finding plastic in the tap water, up to 5 particles or microfibers in every litre of water. And that's just wrong. It shouldn't be there. So, people can do that, but on a more different level, to try and help, the oceans, very simply, don't buy cosmetics containing chemicals such as oxybenzone. Not only is it toxic and dangerous to the environment, it's toxic and dangerous to the wearer of these products. So making lifestyle changes, trying to avoid wearing plastic clothes, go for natural fibers. Think twice about washing your clothes, if you can survive for an extra 1 or 2 days, because the less water we use, the less microfibers are kicked out into the environment. So there's lots of things that can be done, and we list these also on the website.
Okay, good. So I would urge you all to go and have a look at the website and look at what you can do if you wanted to make a change. But shall we see if we've got some questions coming in?
Wait a minute. Congratulations. Make no need, yes,